I'm going to show the solution to this previous exam question. So we're presented with a complex circuit and we are to find the node voltages and also find the power in each circuit element. Okay, so this is a complex problem. We see that we have a current-controlled voltage source here, and that makes it complicated. And something else that makes it complicated is we have two voltage sources that are not connected to each other, so that means we have to use a supernode. So if you want to take a moment and try this problem out for yourself, you can pause the video now, and in a moment I will give you the solution. Okay, so now the first step in this analysis, in node voltage analysis, is to select the ground reference node. Okay, and our typical method is to pick one side of a voltage source. So we could pick over here, or here, or here, or here. In fact, we can pick any node we like, but our guidance is to pick one side of a voltage source because it makes the analysis easier. So if we really wanted to, we could pick this node as well. So now, what we're going to do is we're going to pick the ground reference node over here at the bottom of the 10 volt voltage reference. So the next step is to identify the node voltages. Okay, we've identified one of these node voltages as 0 with the ground reference. Okay, so this means that it's equal to 0 volts. Okay, but now we need to identify the other node voltages. So this is what I'm going to select now. We have VA over here. Pardon me, I wanted to use this. We have VA over here, VB, VC, and VD. Okay, so those are all the remaining nodes. Okay. And our next step is to apply KCL to develop the node voltage equations. So let us do that. So first we notice that VD is 10 volts, so we have that one already. So let's continue. We have for node A, so we're going to create the node voltage equation for node A. So let's just make sure we know where we're talking about. We're talking about here, node A, and when we're doing node voltage analysis, we're going to determine the currents flowing out of the node. We make the assumption that the node that we're working on has the highest voltage and that all the currents are flowing out from it. So now this is what we have for our equation. So for the current going to the right, that's this one, and we have VA minus 10 volts divided by 4 ohms. So that's fairly straightforward. The tail of the current is the node that you're starting from, and the head of it is the node that you're ending up on. Okay? So then we have the current flowing down. So that's this one here. Okay? So that's going to be this term, and it's simply VA over 4 ohms. And that's because we have VA on one end of the resistor and the ground reference node at the other end of the resistor. So that one's also fairly straightforward. And then we have the current going up, so we're going to do this one. So that's this one. And we have our starting point is VA, and then we go all the way through that 1 ohm resistor to VC, so that's what we see on the other side of the equation is VC. So that's VC, and then divided by 1 ohm, which is the resistance. And then finally we have the current flowing to the left. So that's this term. So now we're defining the currents going out as positive, and the 2 amp current source is in the same direction as this reference current, so it's a positive value. So we add that current, okay? And then because we're doing KCL, we need to have that term equal to 0. Okay, so that's how you make the node voltage equation for node A. Let's see the next one. Okay, so now, let's simplify this. Okay, let's get rid of the denominator in the equation. So what we're going to do is multiply that equation by 4 to get rid of the denominator. So we're going to have VA minus 10 plus VA plus 4VA minus 4VC plus 8, all equal to 0. Okay, and then our next step is going to be to collect the terms, and we're going to call that equation 1. So that's our first intermediate result that we have, and we're calling it equation 1. And then we're going to continue. So now we want to write the node equation for either node C or node B. So that's these nodes over here. So there's VC and VB. So now we have a problem because we have a voltage source connected on one of the branches on either of those nodes. So we don't know what the current is going to be flowing through that voltage source, so we need to use a supernode. Okay? And so what we do is identify the supernode, so we're going to draw a circle around it, and we're going to consider that to be one node, and then we're going to identify the currents flowing out of that supernode like this. So from every branch flowing out of the supernode, we're going to have a current. Okay, and we're going to maintain our assumption that this supernode now is the highest voltage in the circuit and all the currents flow out from it. So that's why the arrows are pointing away from the supernode. Okay, so then let's write the equation for the supernode. Okay, so now let's look at the VC side of the supernode. So we're working on this side, and let's look at the current flowing down. So flowing down, we have simply VC divided by 4 ohms because it terminates at the ground reference, so we don't need to subtract any term. Okay, fair enough. So now we're going to go to the left. So that's the second term. So now we see that the 0.25 amps is pointed in the other direction of our reference current, so we're going to have to use a negative sign. So that's why we have this negative sign here. Okay, and then finally we have the current flowing up and around through the 1 ohm resistor. So we have our starting node as VC, and then minus VA on the other side of the 1 ohm resistor, and then divided by 1 ohms. So now what we've got here is the last term on the VC side of the supernode. So then we'll just make a little note saying that this is the VC side of the supernode. Okay? So now let's do the other side. So now the VB side, so now we're working on the VB side, we have a current flowing down through this 1 ohm resistor, and that's simply VB divided by 1 ohms. Okay, it's ending off at the ground reference, so we don't need to subtract anything. And then we have the current flowing to the right, and we see that we have a 2 amp current source with the direction flowing in. So now we have to use a negative sign. So we have this negative sign here. Okay, so now those are the two terms on the VB side of the supernode. And let's just write a little note that that was the VB side of the supernode. Okay, so now what do we do? Well, let's simplify that equation, and let's multiply it by 4 to get rid of the denominator. So then we get VC minus 1 plus 4VC minus 4VA plus 4VB minus 8 is equal to 0. Okay, and then if we collect the terms, we get this equation: minus 4VA plus 4VB plus 5VC is equal to 9, and we're going to call that equation 2, so that is our second intermediate result. Okay, we want to set up basically a system of equations in terms of all of the node voltages, so then we can solve for all of the node voltages. Okay, so we're not 100% quite finished with the supernode. What we need to do is account for now the voltage source inside of there, and so we need to write the dependence equation that's going to relate VC and VB to each other. Okay, so then let's take a closer look at that component. Okay, we have VC on one side, VB on the other side, and a value of 4 IC for the voltage of that current controlled voltage source. So now we can write the equation quite directly as this. So we have VB being equal to VC plus the voltage of the voltage source, whose value is 4 IC. Okay? So now what we can do is develop an equation to describe IC, and IC is over here. Okay, so let's see how we can do that. So let's just examine that part of the circuit, right? So we're just going to extract this and say let's look at that. So we have VA at the top, okay, and we have the IC current flowing through the 4 ohm resistor to ground. Okay, so now we can use Ohm's law to write an equation for this, and that equation is going to look like this. That current IC is going to be equal to VA divided by 4 ohms. So now what we're going to do is plug in IC, value of IC, into IX in the first equation. So we're going to bring that equation down, okay, and then plug IC in there. Okay. And then when we simplify that equation, we're going to get minus VA plus VB minus VC is equal to 0. And that is going to be our third equation. Okay. So now, let us make our calculations to find the node voltages. So we're going to go back and recall our equation 2 and write it out, and then for our algebra, we're going to take the third equation and we're going to multiply it by 4 to put it in a format that's going to work for us to solve for one of the node voltages. So now we can see in this format that the minus 4 VA, if we add these two equations together, the minus 4 VA is going to be zeroed by the plus 4 VA, and that the plus 4 VB is going to be zeroed by the minus 4 VB. So we're just going to be left with 9 VC being equal to 9. Okay? And then from that, we can calculate that VC is equal to 1 volt. So that's our first result. Okay, so now if we plug VC is equal to 1 into equation 1, which we determined before, then we get 6VA minus 4 times 1, which is VC, and that's equal to 2. And we can solve for that to get VA is equal to 1. So now we have two results. So then next, we'll plug what we found for VA and VC into equation 3, and we're going to get minus 1 plus VB minus 1 is equal to 0. And then we can solve that VB is equal to 2. Okay, so those are our results right now. And then we also know that VD is equal to 10 volts, and we knew that from the beginning. So that's our complete results for the node voltages. So now what we're going to do is label our diagram with the voltages, and then we're going to calculate the power in each circuit element. So we've done the first part of the problem here, which is to determine all of the node voltages. So now we're going to find the power in each circuit element, and we're going to need to know basically the voltage and the current, or if it's a resistance, we need to know either the voltage or the current in each element. Okay, so let's see what it looks like when we label the voltages. So all I'm doing here is writing that VC is equal to 1 volt, VB is equal to 2 volts, VA is equal to 1 volt, and we knew that VD is equal to 10 volts. Okay, so now we're going to use this to calculate the powers. Okay, so let's start with the 4 ohm resistor associated with VC. So that's the one we're looking at. And I've drawn the circuit over here to make it more visible. And for this, we can just use the simple relationship that we know, that power in a resistor is equal to the voltage across it squared divided by the resistance, so V squared over R. If we knew the current, we could use I squared times R. But for this, we can solve it much more directly with V squared divided by R. And so we just plug in the voltage across that resistor, which is 1 volt. And if you're having a problem seeing that, then we know that we have 1 volt here, and we know that our ground reference is here, and that's 0 volts, right? So this is 0 volts. This up here is plus 1 volt. So across the resistor, we have to have 1 volt, okay? So that's the voltage across the resistor, and that is where I'm getting this value, okay? It's 4 ohm resistor, and then when we calculate, then we get 0.25 watts as the result. Okay, so, and that is absorbing. So the resistor is absorbing energy, and the property of resistors is that they're always absorbing energy if there's any current flowing through them. Okay, and we also note that because we have a positive value for power, then that's absorbing. Okay, so let us continue. Let us do the second 4 ohms, the ones that's associated with VA. So that's this one here. Okay, well, it's the identical analysis. So I've drawn the circuit as we just to make it a little bit more visible, to isolate it so that our calculations are a little bit more easy. And we have, again, V squared over R, and we know that there's 1 volt across that resistor. So that's 1 volt across this resistor. So it's plus, minus on this side, and that's 1 volt. Okay. And we have 0.25 watts again, like with the previous resistor, and we know that it's absorbing. Let us go to the 1 ohm resistor associated with VB. So that is this one here. Okay, and so I've drawn the circuit, and we use the same formula, V squared over R, and we see that we have 2 volts across that resistor, so it's 2 volts squared divided by 1 ohm, and we get 4 ohms absorbing for this 1 ohm resistor. 4 watts absorbing. Okay, so now let's do this more complicated one. Okay, so now we're looking at the 0.25 amps current source. So we know the current, and to calculate the power we're going to need to know the voltage across that current source. So why don't you take a moment to think about what is the voltage across that current source. Okay, how do we determine it? Okay, well, let's look at more of the circuit. If we notice that this resistor here, so let's just say this resistor here, it's going to have a voltage across it, and we know what the voltage across it is, and we know that the current source is in parallel with that resistor. So let's draw the sub-circuit like this. Okay, so now we have VC is equal to 1 ohm. We have the ground reference node at the other end of the 4 ohm resistor, so we must have 1 volt across that resistor, okay, in the orientation shown with plus on the top and minus on the bottom. So now, since the current source is in parallel with that resistor, we know that there is 1 volt across the current source as well, okay? And that's because they're in parallel. So we can easily make the calculation, and our calculation is going to be some variation of power is equal to voltage times current. Now there's a trick here, and that is that we are using the active reference direction. So we have the active reference direction for this, and so we have to use the minus sign. And so what do we mean by the active reference direction? So what we have here is we have current flowing in this direction, okay, through that current source, and we know the polarity of the voltage, and we have the minus sign on the bottom and the plus sign on the top. And whenever we have that configuration, we know that we're using the active reference direction, and if we're using the power formula, we have to use this minus sign in the equation. So it's minus VI, okay? So this is going to be tricky, so you need to know this. Okay, so then we just plug in our values. We have the 1 volt, okay, for the voltage, and then 0.25 amps, and that gives us, when we calculated, minus 0.25 watts, okay? And this is delivering energy, okay? So it's supplying energy to the circuit, okay? And we know that because of the minus sign. Okay, so then we know that that's, we can just write that for 0.25 amps, and now we're going to look at the 10 volt source. So that is this one over here, okay? Now we know the voltage is 10 volts, but we don't know the current, so the trick is, how do we find the current? Well, think about that for a moment. It's not all that obvious. And so now, if we're thinking about this, let's think about what we want to find. We want to find the current flowing through this voltage source. And now we see that that 10 volt voltage source is in series with the 4 ohm resistor on top of it. And we know that the same current has got to be flowing through it. So that's the same current. So if we can find the current through that resistor, through that 4 ohm resistor, then we'll know the current for the 10 volt source. And what's nice is that we know the voltage at each end of that resistor. Okay, so let's draw it out just to make it more visible. So we have our drawing right here, okay? And then, so we have VA is equal to 1 volt and VD is equal to 10 volts. And we know the resistance, so we can use Ohm's law. And Ohm's law says that the current through that resistor is 10 volts minus 1 volt, so the voltage across that resistor is 9 volts. Okay? And if we divide that voltage by 4 ohms, we get the current, and it's 2.25 amps. And that is the same as the current that's flowing through the 10 volt voltage source. So now we have current flowing into the negative and out the positive. Okay, so again we need to use the active sign convention, and so we have that negative sign, so its power is equal to minus V times I. So we plug in our value for voltage for the 10 volt voltage source, and that's 10 volts, multiplied by the current that we found, and that's 2.25 amps, and we get a result of minus 22.5 watts. Okay, and that's delivering. So this 10 volt source is supplying power to this circuit. Okay, so we're getting closer, and so now let us do the 2 amp source. Okay, where's the 2 amp source? So we're doing this one. Okay, so now this one's not too bad. We know the voltage on either end of the 2 amp current source, and we've drawn the drawing down here. So on one end we have VB is equal to 2 volts, and at the other end we have VA is equal to 1 volt. So we know the voltage across that 2 amp source is 1 volt with the orientation of the plus on the left and the minus on the right. Okay, and now we notice that again we have current flowing into the negative and out the positive. So again we have to use the active reference direction, so it's P is equal to minus V times I. The voltage across that current source is 1 volt, and the current itself is 2 amps, so we get minus 2 watts delivering. Okay, so this current source is supplying energy into the circuit. Okay, it's providing power. Okay, so now let us do the current controlled voltage source. So that is this guy over here. Okay, so now what do we know? We know the voltage on one end of it, it's VC is equal to 1 volt, and VB is equal to 2 volts. Okay, so we know the voltage across it. Okay, so now we know that that's 1 volt. Okay, it's 1 volt in this orientation with plus on the right and minus on the left. Okay, we didn't even need to calculate the current IX to find the value because we already have the node voltages defined. Okay, so then the trick is, what's the current flowing through this device? Okay, how are we going to find that out? So we're going to examine the circuit, and then let us look at the right side of the circuit where we know we have 2 amps going in. So we have 2 amps going in, that's 2 amps, and if we found out what's the current through this 1 ohm resistor, then we can use Kirchhoff's law to find the current flowing into that voltage source. Okay, so let's start our analysis. So then we know that, let's include that part of the circuit in here. So we know that VB is 2 volts. Okay, we know the resistance, so we can calculate the current. And the current is this. It's 2 volts divided by 1 ohm, and that equals 2 amps. Okay, so that's super interesting. We have 2 amps coming in, and we have 2 amps going down. Okay, so that is a super interesting result. Okay, so we have all of the current flowing into that 1 ohm resistor. So that means that we have 0 amps flowing through the current controlled voltage source. So that's a super interesting result. Okay, so if we have no current flowing through, then what's our power going to be? Well, let's just plug in our values. Power is V times I. We know that our voltage, it's 1 volt. However, our current is 0 amps. So our final power through that current controlled voltage source is going to be 0 watts. So it's neither delivering or absorbing power. Okay? So it's not doing anything. In fact, if we wanted to, we could remove this element out of the circuit. Just take it out and it would not affect anything in the circuit. Okay? We can just simply remove it. Okay? So let's just make it more clear, right? We could just remove this from the circuit and it would work exactly the same way. That's what that means. If there's no current flowing through that element, then it's as if it's not there. Okay? So let us continue. Let us find the power in the resistor that is up here. So it's the one that's associated with VC and VA. Okay? So we're going to solve for this resistor. So what we see, as we've drawn it down here, we have VC is equal to 1 volt and VA is equal to 1 volt. So that's interesting because there's 0 volts across that resistor because both ends of that resistor are the same. Okay? So if we plug into our power formula, V squared over R, we get 0 volts, okay, divided by 1 ohm, and that gives us 0 watts. So this element is neither absorbing nor delivering energy to the circuit. So we could remove that as well. So if we wanted to, we could redraw this circuit and let me just show you. So we can take out this and this out of the circuit, and it would, our node voltages would not change at all. Okay, so that's really what this circuit is looking like. Okay, quite interesting. And we see actually 2 independent circuits, one on the left and one on the right. And there can be no current flowing through this branch here, right? Because this is a circuit, so the current through there is 0. So we just have the current flowing around this way, and then whatever the current is doing on the right-hand side. Okay, that's quite an interesting result, a very unusual circuit. Okay, so now let's continue solving. So then we have the resistor on here, and let's just fix this up. We have the resistor over here. Okay, on one side is VA and on the other side is VD. So we've got here VA is equal to 1 volt, VD is equal to 10 volts, so we have 9 volts across that resistor. So if we plug in our values into our V squared divided by R formula, we get 10 minus 1 squared divided by 4, and we get 20.25 watts, and that's absorbing. Okay, that's a resistor. So we have the powers of every circuit element right now. We've calculated all of them, and now what we should do is make sure that we have energy balance so that it's a cross-check to our calculations. So we know that all of the powers should add up to 0. Otherwise, we'd have power being lost or being gained from outside of the system. But we have a closed system here. So let's add up all of the powers. So we can sum them all here, so we're summing all of them, okay? And now we want to see what is it equal to, and all of that, if you calculate, it's equal to 0 watts. So there is energy balance. So we have confidence that we've done this circuit analysis correctly. Okay, so that's a complicated problem, and I hope it illustrates some of the circuit analysis, or brings it all together. We did a super node, and we had a current-controlled voltage source, so it's a complex circuit, okay, with some interesting behavior with no current flowing through some of the branches.